what's the trick? What's our new trick here? Well, let's write down the rule first, our differentiation. So the derivative with respect to x of what? So, okay, so cx to the n equals
Cnx to the n plus 1.
Okay, good. And so the way we want to maybe remember this then, what's the working rule? Well, if you're differentiating a power of a variable, you just take the exponent down front and subtract 1, right? That's it. So this becomes pretty simple, right? What's this going to give us then? What's the first term going to give us?
Negative 2x to the third.
Okay, good, because I've already got a negative 1/2 there, times 4 is negative 2, and then I subtract 1 from the exponent. Next term.
9 squared. And then minus 2.
Minus 2, good. So does that work? I mean, this is overkill, but do we really need, I mean, so we could say, what if n is 1? So for example, if I want to take the derivative, and this is way overkill, we don't need to do this, but I just want to show you it's consistent. The derivative of 3x, well, that's 3x to the 1. So what does the power rule tell us? We get 3 times x to the 0, anything to the 0 is, so we just get 3, don't we? Right? Which we knew, right? Because the derivative of x is 1, right? With respect to x. Okay, let me show you another way of looking at that. And it's all real consistent. So we can use the power rule, or we could even just say this, right? We could say the derivative of 3x with respect to x, and that's how we'd say that. The derivative of this with respect to whatever we'd call the variable of differentiation. Whatever the variable is that appears on the bottom, okay? We're going to look pretty soon at some instances where the variable of the function doesn't match the variable of differentiation, okay? And that comes up a little bit later, all right? That's called the chain rule, and we're not quite there yet, but it's not far off. What if we just rewrote this? So we're going to take the very same problem, but instead of applying this rule, just look at it kind of algebraically. So the derivative with respect to x of 3x is really the same thing as saying I can pull the 3 out front, right? 3 times dx dx. Well, what does dx dx look like? 1. Yeah, and it is. Yes, ma'am.
I just don't even understand how we got the negative 2x to the third plus.
For this part right up here?
Yeah.
Okay, so the way we get that is because we know if we wanted to make a little bit of a short list of what are the derivatives that we know. We don't know very many, right? We don't know very many at all. At this point, we only know, really, probably, I guess we could maybe eke out 3 that we know. Let's just write those down. So we know that so one we know is that the derivative of a constant is what? What's the derivative of a constant? If we think about it, and we looked at this a while back in terms of a graph, right? It's a slope, isn't it? So if I have the line y equals c, that's a horizontal line. What's the derivative going to be? Right? Remember we looked at some examples where if I give you the shape of a curve, and let's just go back and revisit this real briefly. So what if we have something like, here's the function, we'll call that, I think we use this one, so f of x. Now let's make a graph of the derivative of that function. Right? Derivative, remember the value of the derivative equals the slope of the function. So what's it going to be? 0, right? So if we were to graph the derivative graph would just look like it's going to have a value of 0 everywhere, right? The derivative of a constant is always 0 because it's not changing, right? We're asking about the rate of change of something. Well, does a constant change? No, it doesn't, right? So there's one that we know that we've never officially written down, we can just kind of talk through. Well, now we're getting to a point where we want to start to maybe try to assemble all the stuff that we sort of talked through and conceptually, and we looked at examples like this, and we did some basic problems using limits as derivatives. We're going to try to pull all that into one very simple process now. All that stuff just gets reassembled into a list of derivative rules that we can just follow, right? So one of them is that we can pull back from all the theoretical discussions we had. If we try to take the derivative of a constant function, we get back 0, okay? Well, here's another one. You know what, I can see where maybe, does this make sense? If we said, if I wrote it in this context, I bet it would. If I said f of x equals x, what's f prime of x? We took the derivative of that. Does it make sense that it's 1? Okay, because if we were to graph the function y equals x, what does that look like? Well, that's just a slope, that's just a line, y equals x with a slope of 1, right? Okay, so now we can come back and we can turn that into a rule if we want to. We can say the derivative with respect to x of x is 1. Okay, we added this big fancy rule yesterday called the generalized power rule, which says the derivative with respect to x, and let's not even throw the c in there. We can add that as kind of an afterthought. The derivative with respect to x of x to the n is nx to the n minus 1, right? You just bring the derivative, or bring the exponent down front and subtract 1. And if we want to kind of soup up that last one, we could, just so we can make it more general. We could add a constant in there too, right? The constant, the moral of that story is, if I'm taking the derivative of a constant times something, well, the constant we can just pull out in front of the derivative and it just stays there, right? It doesn't do anything, okay? So what I want you to see now is that these two previous derivatives that we've sort of talked around, and we've never written them in this form because we haven't been ready to, but those are just specific cases of this rule, right? Let's get rid of that c again. What case is this one right here? Well, what's the power of x? 1, right? So all of these things really come from this one powerful rule, right? So if we say if n is 1, then we bring the 1 down front times x to the 0. Well, that's just one of our basic exponent rules. Anything to the 0 is 1, right? And so this is just the general power rule where n equals 1. How about this one? That's one that's a a little bit bizarre. So that would be like saying if we're going to, it fits the power, it's consistent with the power rule. This would be like saying the derivative of c times x to the 0 to start with, right? Does that make sense? So then if I'm going to start off with 0 in the exponent, if I bring that 0 down and multiply, getting 0 for an answer, right? So everything that we do up there is consistent with the general power rule. It's just that these two are ones that we come to see as being so basic that we just don't even really, we just think of them as, okay, yeah, we know what that is. The derivative of x is 1, and the derivative of c is 0, right? Those are ones that just kind of will be real obvious to us as we use them more. This is where we have different cases that require a little more attention. Okay, so then on this previous page, does that make sense how we're getting from there to there, right? The exponent we're starting with is 1. And so the rule we're using is we're just using this one, right? We're going to bring the 1 down times the 2, and then we get x to the 0, which is 1. Right? Notice that when we differentiate, notice the pattern. Notice what's always going to happen to the exponents. The exponents are always going to drop by 1 every time. Okay, when we differentiate a power function. Okay. What's the moral of the story? Really going from yesterday to today, dealing with this problem is just that we can differentiate term by term. There's a bunch of stuff, and you guys really do need to, and I mean this, you really do need to go through section 2.2 in the book and scan through that and just make sure that, I'm just going to pull it up on the overhead for just a second. These are some things that I'm just going to take for granted that you're going to have looked at a little bit after, not before today, but after today.
No, it makes sense. It's just weird that it
What is this chapter? Chapter 2, right?
I think you said 2.2.
2.2, yeah. So here's the book, right? When we're going through the book, let's just take a second and let's just look at sort of what are the things on here that are kind of important. So when you're reading, now this is the one we did a little bit earlier, right? This is all the limit stuff, and I feel like everybody's in real good shape on that. So we've got these definitions of derivative based on the two different forms of the difference quotient. I don't think there's a lot in here that probably is going to be different than what what we've done in class. I don't think you need to read that section if you haven't already. Differentiability implies continuity. We did all that stuff in pretty good detail. But when we get to section 2.2, notice all the blue boxes. So there's one right there. There's the constant rule, right? Okay, we wrote it on the board, but you're going to want to maybe, and I'll hand out a sheet to you also. If I don't put it up today, I'll put it up tomorrow on the site on Moodle, where we'll just have like a sheet, a PDF downloadable document that's got a growing list of all the derivatives that we know. After today, we're going to know, a handful. We'll gradually add to that list as the year progresses. Okay, power rule, right? There's the one we talked about yesterday. Okay, but constant multiple rule. So we just combine those two, right? If I'm taking the derivative of a constant times a function, we can just pull the constant out front and just take the derivative of the function part, right? And you already get that. That's what we did on that problem at the start of class today, right? Sum and difference rules. Okay, this is also stuff that you guys I know you intuitively get, but I'd like you to read that within the context of a textbook too, just to see that officially we can do this stuff. If we're taking the derivative, what does this part right here say? Let's just focus on the importance of this little blue box right here. Okay, what's that giving us permission to do? We're already doing it. But what's it officially telling us? Yeah, okay, here it is. It's in the contract. You can do it. Say it again. If I'm doing the derivative of a sum of terms,
you can find the derivative
separately. Now the way we're going to say that, the way these are the words that describe that. It's important that this kind of makes sense, because we can say we could differentiate term by term, right? Meaning we can take them one at a time, which is huge. We don't have the benefit of being able to differentiate factor by factor, unfortunately. When we have to differentiate products of factors, it's not that simple. And for that reason, when we get to that point, we're going to really focus on that exception to the rule, right? We'll have to use something called the product rule, which is different. But when we're doing sums or differences, yeah, just take them term by term, right? No big deal. And then, okay, so that's, there are just a few little things that kind of fill in the blanks there. I don't think you don't need to read this thing word for word, but you do need to be able to navigate a math book. And I feel like that's something I have not done a good enough job of in the past, is made people, and I'm going to, darn it, I'm going to make sure everybody has to do that a little bit this year. You got to get used to reading a math textbook, because it's a language of its own, and you're going to do a lot of it in college. So, I don't know how I'm going to enforce that, but somehow I'm going to make sure that, like, I might give you a couple assignments throughout the year where I'm just going to say, you got to do this out of the book. You know, this one you just got to get used to doing something out of the book. So as hard as that's going to be for me to do, it's going to be like pulling teeth for me not to. But I'm going to make you, it won't be a hard one, but I'm going to make you got to do some stuff like that. Okay, so we've got this growing list of, where's my growing list of derivatives? Right there. Basic derivative rules. We've only got those ones right now, right? And then the sum and difference rule, right? We can differentiate term by term. Let's add another one to the list. Before I go any further, though, does this page make sense? Okay. Well, prove it. Okay, do this. Do that. That is just a kind of a tricky application of the power rule. I want you to show me how though. Here's our power rule. So on problems like this is a really important step. You have to rewrite the function in a way that makes it applicable to this rule, makes this rule applicable to it. I call that pre-writing the function, right? So how am I going to rewrite f of x so this applies more obviously? Okay, good. I'll write it as, I could write it as 3 times x to the minus 1. Now that looks like a power, like a base to an exponent, right? And so what is, if that's the case, if that's f of x, then what's f prime going to be? Okay, negative 3x to the negative 2, which we could rewrite as negative 3 over x squared if we're going to write it in terms of positive exponents, right? And you'll get to a point fairly quickly where, you know, you'll be able to just maybe just jump straight to that. But there are those intervening steps. Okay, how about something like this one then? How about if we've got these different notations? So what if we have y equals the square root of x? dy dx equals what? How am I going to pre-write that one? Okay, good. We're just going to write that as x to the 1/2 power. And so what am I going to get? Seth, what do I get if I differentiate that using my power rule?
X over 2.
Okay, but now go through the whole thing, right? We've got to follow. So I've got x to the n.
Yeah.
So I got to bring the n out front. And then x to what power? Okay, yeah, 1/2 minus 1 would be negative 1/2. So what's that look like? 1/2. And then x to the minus 1/2 is, if I write that as a radical, for example, what's that look like?
1 over radical x.
Okay, 1 over square root of x. So I could just write this as 1 over 2 radical x, right? Everybody see that? Yeah, I'll leave it there for a sec, right? We just followed the rule. This part right here is us just, you know, being rule followers, right? And then at the end, we're just going to rewrite it in a more convenient way. Okay. Let's try one more of those. There's another notation. That's our abbreviated notation for a derivative. If we, kind of makes sense, doesn't it? We defined, like if we said f of x equals something, then our functional notation is f prime is the derivative. Well, shortcut for f of x is y, so y prime is the shortcut notation for the derivative, for f prime of x. Okay, how about that one? How am I going to rewrite it? Before I even put the y prime there. How could I rewrite that one as some constant times x to a power? Negative 2/3, good. Okay. Remember, the index of the radical is the denominator of the fractional exponent, right? The 2 would be the numerator, okay? And so then, what's y prime going to be? 4 times, okay, good, so 4 times, there's, I heard negative 8/3, so 4 times whatever the exponent is, that's going to come down front, times x to what power? What's negative 2/3 minus 1? Negative 5/3, isn't it, right? Negative 2/3 minus 3/3, minus 1 would be negative 5/3. Okay, and so then I could write that, if I want to write this as one big fraction, got negative 8, on the bottom I've got a 3, and then what is this just becomes? X to the 5th. Or if I want to write it as x to the 5/3, but if I want to write it using a radical, that would be my final answer. All right. Okay, so how about then, let's add another rule. We're gonna add just 2 more today to our list. And then we'll end up with at least something to, well, fairly good bag of tools to do some stuff with. So let's do a sine function. Okay, and so this is a model for what we do a lot in math and in calculus. We're gonna start from basic principles and try to come up with a formula, something that we can use all the time, which is useful. So we want to calculate the derivative with respect to x of sine x. Okay? So let's start with, let's use the delta x formulation this time, how about, right? So how do we define the derivative of a function in terms of a limit, the difference quotient with delta x's? Let's go ahead and start general. So let me just write it down. I never leave myself room for that. So our general formulation is dy dx, or f prime of x equals limit of what? F of minus f of x over as. Okay, so then for us, we're taking a limit of, what's f of x plus delta x? Okay, minus okay, and obviously if I evaluate it now, I get 0, 0, right? So we need some more work. Well, in this case, the more work is just some trig stuff, right? Good trig review. So what's our expansion of sine of x plus delta x? Do you remember that one? Okay, do you remember what, here's how I remember this one. I've always got my own little, so I don't want, once again, I don't want to waste those brain cells memorizing a bunch of stuff. But I do know, here's one we use a lot. We know the double angle formula. What's sine 2 theta? 2 sine theta cosine theta, right? Everybody agree? That's one, you'll know that one pretty soon. We use that one a lot, right? 2 sine theta cosine theta, okay? So then that tells me sine 2 theta is the same as sine theta plus sine theta, right? So what did we do there? What did we do? Well, we did this, right? We said this part right here, let's just do this part in the green box. It's got to be sine of theta, cosine of theta, plus, not minus, because they added up and I got two of them, right? So I always remember I'm going to get sine x, sorry, this is right. Sine x cosine delta x plus the flip, cosine x sine delta x. Because in this case, up here, they were both theta. So I get sine theta cosine theta plus cosine theta sine theta gives me 2 of that product. Right? That's how I, in my mind, I always remember. Yeah, it's hard to remember. Is that going to be a plus or a minus? Which one goes with which? You know, there's a lot of, we don't use them that often. But because they have to add up to give me 2 in the collapsing case where both angles are the same, I have to get 2 of the product. So they must add up. That doesn't make sense. Don't worry about it. Just remember it. Just remember them. That's the other choice. Just remember them. Minus sine x all over delta x as delta x goes to 0. Okay, so now we've got some stuff to do to work with, right? What can we do with our numerator here? Okay, so there are a couple terms that have sine x's in them, right? So how about if we regroup these? So let's write this maybe as the limit of, let's go ahead, the first term and the third term both have sine x's. So let's go ahead and write this middle term first. Cosine x sine delta x plus sine x cosine delta x minus sine x, right? All over delta x, but we're going to go ahead and group those together, right? Okay, so if I'm taking the limit as delta x approaches 0, we could break this up into 2 separate limits, right? At least in our mind. And I'm going to write them out separately. So this is the plus sign that's going to join the 2 limits. We get the limit, well, this limit, plus this other limit of all that stuff, which we'll get to. Let's focus on the first one for a second. Do you see anything helpful there? Okay, the sine delta x over delta x in the limit as delta x goes to 0 is 1. Okay, this is the part that I want you to see here. What about the cosine x? As far as the limit is concerned, is x a variable or a constant? It's a constant, right? Because the part that's changing in the limit is the delta x. Delta x is approaching 0. X isn't doing anything, right? So what's the limit of cosine x as delta x approaches 0? Cosine x, right? Right? The cosine x is not changing. And this comes from, if we were to go back a chapter, I'm going to remind you where this comes from. If we were to go back a chapter, we said that the limit of c times f of x as x approaches, x approaches a, let's say, is the same thing as saying c times the limit of f of x as x approaches a. We could pull the constant out front, right? Because c must not have had any x's in it, right? Well, in this case, it's not x, it's delta x we're concerned about. This isn't a cosine of delta x, it's a cosine of x. And so as far as this limit is concerned, So as far as this limit is concerned, delta x is the variable of the limit. This cosine doesn't have any delta x's in it, so it can come out front, right? So then the first limit, and let's just knock this one out first, and then we'll go deal with the second one. What are we going to get? Cosine x times the limit of sine delta x over delta x. As delta x goes to 0, what's that limit? 1, yeah. Right? Okay, plus whatever we get over here, right? So then we end up with cosine x plus the result of the other limit. Well, let's focus on the other one, okay? Now think about the two special limits we have. We're much more familiar with the limit of sine x over x as x goes to 0, or sine theta over theta as theta goes to 0. But the other one, remember that one? That one was the limit of 1 minus cosine theta over theta as theta approaches 0 is equal to 0. Okay, good. So let's write that up here, Randy. This is our other standard trig limit, right? So we almost have that, right? Instead of theta, we've got a delta x. But I've got them backwards. This is the one that if I were to factor a sine out of this, I would end up with cosine theta minus 1. Agreed? I want 1 minus cosine theta. And so I'm going to factor out a negative sign instead. Okay? Everybody agree? So we're going to take the limit of negative sine x times what's left over. 1 minus cosine delta x, right? All over delta x as delta x goes to 0. Well, in the limit, as delta x goes to 0, remember the sine x is just a plain old sine x, right? That's constant, that doesn't change. But what does this limit go to right here? That goes to 0, right? And so this second term conveniently goes away. I get sine x for the second term. I get negative sine x times 0, which is 0. So my answer is cosine x. Okay, well, what do we start with? The derivative with respect to x of sine x is cosine x. Okay, so we can add that. Let's go back and add that to our list. Where's our list? Right there. Okay, so another entry on the list here. Derivative with respect to x of sine x equals cosine x. I'll go ahead and give you this one for free. The derivative with respect to x of cosine x equals minus sine x. Okay. And we could have proved either one of those or both of them by the same process. But now we've got, technically we've got 5, but really we've just got 3 because these two are contained in the power rule. Okay? Well, we're getting lots of stuff here, aren't we? So how much time we got? Oh, 7 minutes. That's an eternity. That's an eternity. We can do all kinds of stuff in 7 minutes. Okay, so let's try, how about... Okay. Do that. I think we missed a day though.
It was good, it was Monday.
What's that?
It was good, it was Monday. It went off the language arts.
Oh, okay, so we didn't, all right.
Yeah.
We gotta keep the string alive here. Okay, so what are we thinking on this one? The fact that you got two terms is no big deal. I'm just gonna differentiate term by term. How do I treat the first one? That's really the sneaky way. How do I write that as a power?
3x to 1
Ah, okay, so I'm gonna write that as a 1/2, right, square root, okay. And so
Oh wait,
then,
is that the third?
so no, okay, that's supposed to be, yeah, it's supposed to be 3 times the square root of x. I can see how you might have thought that was cube root. So 3 times the square root of x. So then, what am I gonna get when I differentiate? X to the negative 1/2, good. And we might rewrite this. How about the cosine x? What's the derivative of cosine x? Negative sine x.
Or plus sine.
Right, and so then if we want to simplify this, this is just going to give me what? 3 over 2, good, square root of x.
Plus sine.
No big deal, right? Okay. Make sense? Yeah, that's it. Okay, so then this trick, this saves us so much time, because that was getting a little tiresome, a little tedious, just going through that limit process every time. But now we can do problems that would have seemed pretty darn hard before. Like, what if we want to find tangent line to y equals sine x at x equals pi thirds. Right, so if I were to draw a picture, this just looks like my sine graph does what starts here, just goes. And so out here at x equals 1, remember from 1 complete wavelength is going to be 2 pi, right? So that's going to be pi halves. So pi thirds is going to be something like maybe right there-ish, right? What are the coordinates? Well, if I want to find the tangent to the curve at this x value, what are the ingredients of a line? Point and slope, right? So let's take care of the point first. When x is square root of 3 over 2, what's y? I mean, sorry, what did I say? X is pi thirds. I kind of gave it away, huh? Well, actually, no, I didn't. What's y? What's the sine of pi thirds? Well, I guess I did. So remember, not square root of 2. Pi thirds is the one up there, right? Square root of 3 over 2, right? That's good. I guess I kind of gave it away. Right, so there's my point of tangency. What's the tangent line going to look like? Well, we already get an idea. It's going to look something like that, right? Okay, so we know the point. Now we just need a slope. But that's easy for us now. We've got a rule for this, right? How am I going to find, the slope of the curve? That's given by a derivative. That's the job of a derivative, is to tell us the slope of a curve for any value of x that we plug in, right? So what is y prime? Cosine x. Okay, so we're trying to find y prime at that x value. Yeah, so cosine of pi thirds, what is that? 1/2. Yeah, it's 1/2, isn't it? Oh, I know why. I know it's wrong. That's pi. Pi half. So we'd be right there, wouldn't we? I got the wrong spot, right? So the slope, yeah. So the slope would be 1/2, right? 1/2 at that point, and that's all we need. I've got a point. I've got a slope. Solve for b, and we got it, right? That would be a big deal. Man, we're getting smart. Holy shit.
So,
I'm so bummed.
Okay, I'll put up